That's so scary. I know, that's not even my closest family. That's yeah, this is like at least 50. I think the college children are pets. It is actually
Okay, you guys. We're on Friday, and we're pretty much on schedule. We're going to talk about cylindrical and spherical coordinates, triple integrals in cylindrical and spherical coordinates today. Got a few homeworks here back to certain people. I feel like you guys probably have a pretty good idea of how to do cylindrical coordinates, even though we haven't addressed them explicitly. And yeah, that's everybody. Okay. So I'm going to give both of these guys pretty short shrift today. The real new information is, what does dV look like, the volume element? What does it look like in these new coordinate systems? And then we're just going to do a bunch of problems. Before I do that, two other things I want to do. I want to answer questions that you might have on the current homework. And then a lot of people have been coming to me, asking about the math major and the math minor and so forth. And you guys have pre-registration coming up, not next week, but the week after. And so what I thought I would do is briefly talk about the math major at Whitman College for maybe 10 minutes or so. Before I do that, though, are there questions on the current homework? Lila?
On webbook number 4, that's the one with like the spinny shape.
Okay.
I got one of the Z limits, but then it did not accept any kind of limits.
Well, let's have a look here. So, triple integrals number 4. All right, so we have the base of this figure is a 90-degree cone, and the cap of this figure, at least, I don't know if your numbers were different, but mine is a sphere of radius 8. What you need to do is, first of all, the Z range, as you probably figured out, is going to go from the cone up to the sphere. So those are the lower and upper limits of integration, respectively. The lower limit, it's going to be Z equals the square root of x squared plus y squared, right? That's the lower surface for Z, and the upper surface is going to be like Z. In my case, Z equals the square root of 8 minus x squared minus y squared. All right. So now that you've figured that out, what the top and the bottom surfaces are and what the Z range is, you now have to shift your focus into the xy plane and see in what region in the xy plane is all of this happening. How do you figure that out? Hannah?
Well, you find where they intersect.
Yeah.
It's going to be like a circle, and you project that onto the x-axis.
So you can rotate this guy up and look down from above, and you can see that this is a circle of radius 5-ish. But even if you don't believe the picture, what you can do is take the two equations. You can take the two equations, so Z is equal to the square root of 8 minus x squared minus y squared, and set that equal to this other equation, x squared plus y squared. You can square both sides. You can move the x's and the y's to the right. And what you end up with is a circle of radius 2 centered at the origin. And then you just have to do the remaining limits of integration based on that circle. Nick?
I did the exterior, I just looked at the picture to
Uh-huh.
try and find the exterior, like the X limits.
Yeah, let me pull that up.
And since it goes from -5 to 5, I suspected those would be the limits of integration for the exterior one. Like
Yeah.
A and B, but it said that was wrong.
Yeah, that is interesting. What did I just get? 1 or something, or 2? So maybe the sphere, maybe we should look a little more closely, sorry, not at the sphere, but at the cone. Oh, it does say it's a 90-degree cone, and the radius is 8.
Well, one of the things you can do for that is just convert it to polar. So like Z equals R, and so you can see there's like a right triangle of hypotenuse 8, and then the sides are equal. So it'd be like 8 over radical 2 and 8 over radical 2.
Right. I'm also seeing Sorry, say that again, Hannah. 8 over, so you convert the bottom one, so the bottom cone is Z equals R, right?
Yeah.
And-
So then if you just look at it sideways, you can see that the radius is 8, because it'll go out to how far the sphere is, which is radius 8.
Right, that's
And
8.
So that angle there, or that side will be 8, and it makes a right triangle. So if you go straight down, it would be 8 radical 2, and 8 radical 2 is each leg.
Yeah, so why didn't I just get that when I, what did I do wrong here, I guess is my question. When I set those two guys equal to each other, I should get the same thing. Is that what it is?
Oh, no, it is.
Ah, there you go. That's what I did wrong. Thank you. So let's fix that. So that should be 64 there. Now we're all better. Yeah, I was stuck there. 64, 64. And then now the 2 goes over. That's still 64. And now this is 32. And whatever that is that 4 times 8? I don't know. What's the best perfect square? 4 root 2, I guess. Yeah. So R is equal to 4 root 2. Yes, I feel much better now. Does that answer your question? Was that you, Nick? Yeah.
Yeah, I think so. So
Okay.
the picture's just wrong.
No, the picture's right. Ish.
It doesn't touch the edge, right?
It's close enough, I guess, is what I'm saying.
I mean, it
Yeah.
looks like it touches the very edges. And can we look at, what is the next one, 5?
Also, the number is probably not that precise, because the cone is like.
Yeah, I noticed the
has all
cone.
flat sides, so
Exactly, and it doesn't even really
not
seem.
that many data points,
Yeah.
so it's less precise.
So this one, Nick?
Yeah, did it just want us to evaluate the integral and then say what it was, or is there a way to visualize this that?
No, not to evaluate the integral, to analyze this thing. The sign of an integral is closely related to the sign of its integrand. So if you're integrating the set W, right, you're integrating the set of points between this right cone, this right angle cone, and this horizontal plane Z equals 2. Does everybody see that? Okay, so all of the points, in a way, all of the points that are in W at some point or another end up inside this integrand. Every point inside that region, one of the things that they have in common is they're always above the cone. So every point in the region's Z coordinate is going to be bigger than that cone, which means Z minus the cone is going to be positive. That integrand is positive everywhere. The integral has to be positive. Let's look at the next one. This is even simpler. This is an exponential function. Exponential functions are always positive. Therefore, the integral is positive. And the last one here, again, W is this region, and what you know is that W is completely under the plane Z equals 2. So what do all those points have in common? Their Z coordinates are all less than 2. And so that integrand is negative, and the integral is negative. So one way that you can look at an integral, or one way to think about these integrands, is at some point during this process, every point in W ends up in here. And what they all have in common is their z-coordinates are less than 2. And so what you end up with is a negative number times a little piece of volume. Volume's always positive, right? Negative times a positive, add up all those negative numbers, you get a negative number. Other questions? Go ahead.
Yeah, on the first web work, I keep getting like the correct answer, but I'm off by a negative. So I was just wondering if there's some like sort of common error that would yield that.
I guess my question to you is, which one of these, when you did your z limits, what was the lower limit, what was the upper limit for you?
The lower limit was the paraboloid that's above this xy plane.
And there you have it.
Okay.
They're both above the xy plane, I guess.
The one that's concave up.
Yeah, so the concave up one is the bottom, is the lower limit.
Yes.
And the concave down one is the upper limit?
Yeah.
Did you make sure that you did that? So z goes from the bottom, z goes from this guy, which opens upward, to this guy, which opens downward.
Okay.
And if you reverse that, you're going to introduce a minus sign.
I see. Okay.
Any other questions? All right. Let's talk a little bit about the math major at Whitman. So, I might be a little bit biased, but I think the math major is probably like the perfect liberal arts degree. And I say that slightly facetiously, but slightly seriously too. Right? A liberal arts degree should explore a significant area of human thought. And I think it's inarguable that mathematics is a significant area of human thought. It's thousands of years old. It has had probably more impact on human events than any other single discipline. And it's extremely rigorous. I don't know. I mean, I can't say enough about it, I guess. And then bonus on top of it is you can often find a job when you have a math degree. So I mean, it's just the best of all possible worlds. So let me talk about what you can do after Whitman. So I've had several students in recent years. In fact, together these students and I have kind of carved out a new career path for Whitman math majors. I've had 3 students in the last 3 years go off to engineering schools and get engineering degrees. 2 of them went to WSU and did electrical engineering. 1 went to Montana State and did civil engineering. One of the things that they all had in common was they all majored in math here, and they took a couple, maybe 2 core engineering courses down at Walla Walla U, which is in College Place here. And many of you may know this, many may not, but if you're a full-time student here, you can take courses for free down there. And so you can major in math here, and you can do like 1 or 2 core engineering courses, because they have an engineering program down there at Walla Walla U. And now you're really well positioned because you have all this mathematical maturity and all this mathematical experience, and you've got these sort of core engineering courses that engineering schools make all of their majors take. And you go to WSU and you say, okay, I want to be in the electrical engineering program. And they're generally happy to take you. And maybe you'll have to take 1 or 2 more remedial type engineering courses, but not too many. And both Henoch and Jared both finished masters in electrical engineering coming out of Whitman with just a couple of courses from Walla Walla U. Both finished them in 2 years, no problem. And I don't think either one of them paid for their degrees. They go and they did they did teaching assistantships or research assistantships, which paid for tuition and actually gave them money to live on too. So you can do that. You could go teach high school, which is something that several students of mine in recent years have done. There's a really nice program at Central Washington University, run by Chris Black, who she set up this program where you graduate in May with your math degree, and then during the summer after you graduate you take some education courses, and then during the fall you take some education courses, and then the next spring you do student teaching, and then the next summer you do some more teaching courses, and then that fall you're in the classroom certified secondary ed in Washington State. So essentially a year and a summer after you graduate, or a year and 2 summers. Anyway, a year and a summer after you graduate, you're in the classroom. So that's a possibility. And there are lots and lots of programs nationally and in Washington State that'll actually pay for that. It's not terribly expensive anyway, and there are lots of programs that'll actually pay for that if you commit to, say, teaching for X number of years. So there is that. You could get a PhD and teach college. You would be surprised. Now, you can't sort of, maybe you can, I don't know. I don't have any direct experience with this, but if you look at a company like Amazon, or you look at a company like Walmart, and you think, oh, Walmart's a department store, or Amazon is, an online store. That's not really what they are. Both Walmart and Amazon are supply chain management companies, right? They don't make any of the stuff that they sell, right? They don't produce any of the stuff that they sell. What they do is they go contract with people to build stuff, and then they move that stuff from point A to point B all over this country. What they have is a supply chain network. And if you're a mathematician that has studied networking, optimization, logistics, operations research, and you can get in there and you can look at Walmart's supply chain, or you can look at Amazon's supply chain, and you can save them 5% on fuel costs just by tweaking this or that, they're going to love you. And they pay you lots of money to do that, because you can, for your pittance salary of $150,000 a year, you can save them millions and millions of dollars every year on fuel costs because you design their network a little bit better. So they're happy to pay you gobs of money to look at their network. You can't really get to that position in Walmart or that position in Amazon right out of Whitman. What you'd have to do is go on to graduate school and do a PhD in a math department, either in operations research or optimization or logistics, something like that. But these are all highly mathematical programs. Jared, the kid that I mentioned who's at WSU, has finished his master's in electrical engineering, is now doing a PhD in electrical engineering. And I talked to him a couple of weeks ago, and it's not electrical engineering. What he's doing is working on national power grids, actually regional power grids. And what he's really doing is optimization. Now, granted, he's doing it in the electrical engineering department because that's where the application is, but the kinds of things that he's doing are very mathematical. For example, even in the Northwest, we have a really good situation for a dynamic power grid, where we have the dams, we have lots of wind power, we've got fossil fuel power. Fossil fuel power is reliable. You can generate as much power as you want with fossil fuel just by cranking up the amount of coal that you're dumping in or what have you. But dams only generate power at certain peak times of the year, and wind only works at certain peak times of the year. So what you want to do is, you've got all these sources. Some of them are constant and very much under your control, and some of them are variable and very much dependent on weather conditions and what have you. And you want to optimize this network. How much carrying capacity should I have from here to here, from here to here, and when should I switch over, and how can I do that in a way that's the most efficient so that I don't use as much fossil fuel, that kind of thing. That's the kind of stuff that Jared's doing, and he started out with a math major, and frankly what he's doing is continuing to develop mathematics in that area. Another big area is statistics. So we have one statistics faculty here, Professor McConville. A big area of employment after Whitman, if you've done a lot of stats, is something called actuarial sciences. Actuarial sciences are where you assess risk for organizations. For example, finance companies use actuaries to decide whether that, how much money they should put in this fund, how much money they should put in this fund, how much they should put in this fund. What actuaries do is they sort of study demographics and trends, and they try to predict, what sectors are going to be good and what sectors are going to be bad, and what are the risks of leaving your money here versus here, and so forth. In the insurance industry, which is another big employer of actuaries, insurance companies, they have this money that comes in from premiums that they invest. And then they have all these people out there that want that money back when they go and have medical services. The question is how much money you need to have in reserve so that you can pay these claims, and how much you can lock up in assets that maybe are going to generate stuff over time. But if I go invest in some land somewhere, then that's no longer a liquid asset, right? And if I have a lot of claims, I've got to suddenly go out and sell that land so I can pay these claims, right? And so the actuaries go through and look at all that, and they try to decide, well, what's the risk of a whole lot of claims right now, and how much should our premiums be to balance that out, and what kind of non-liquid assets should we be into? And it's really, it might sound kind of dry, but to be honest, you go into work every day and you've got this, you're modeling these things, you've got all these different variables, you're problem solving all the time. It's a really interesting area of work.
Highest quality of life out of any job in America.
Yeah, because you're working 9 to 5, you're not carrying around a beeper or whatever and getting called in at 3 a.m. to deliver a baby or something like that. You're working 9 to 5, you're getting paid buttloads of money, and you have really interesting problems to work on every day. So that's what you want, right? Happy, lots of money, and yeah, okay. Another thing you can do, and I did this also, while I was in college, I started working at a lab at the University of Pennsylvania, and then after I graduated, rather than go straight into graduate school or go into teaching high school, I actually worked in this lab for a year, and I had a good time there. And if you graduate with a math degree, or really some kind of technical degree like physics, or where you can actually do something with numbers, I worked for this psychology professor at University of Pennsylvania. He was running all these experiments on retinal physiology and that sort of stuff. And I went in there and said, yeah, I can take a column of numbers and make a plot. And he's like, you're hired. It's those people live in fear of mathematics, and so if you can sort of wander in there and just kind of make a plot and fit a curve to it, they're going to love you to death. And that's what I started out doing, and then very quickly I was running experiments, I was helping them with papers and stuff like that. So you can use your math degree to sort of get into places, and then you're a math person. You can think, you can grow into that job. So a gap year is good. Ultimately, though, working as a lab tech is a dead-end job. You're not going to get anywhere until you advance your education. So it's good short term, but those jobs are everywhere. If you go to the human resources webpage at the University of Washington, there are just dozens and dozens and dozens of lab techs where you could, literally this summer, if you wanted to, you could go and try to sign up, but try to get a job as a lab tech there and develop a relationship with a researcher particularly in psych or soc or something where they fear math. Yeah. Another thing that you could do this summer is there are these research experiences for undergraduates in math. There's a whole web page at the American Mathematical Society, and there are dozens of opportunities here where you would go and you would live on these campuses and you would work with other undergraduates on research problems. So I encourage you to go look at that for undergraduate activities. Other undergraduate activities, so if you're a math major here, because we're such a small school and we don't have a ton of math majors here, our upper division offerings are fairly limited. I mean, they're enough to get you into graduate school, but there's not a whole lot of variety. So something that you can look at if you want to kill two birds with one stone is the Budapest semester in mathematics. This is a study abroad program that is very well respected in the worldwide math community. If you've participated in this thing, you've got a real people are, it's very attractive to graduate schools if you've participated in this program. And it's also a nice way to supplement what you're learning here at Whitman. So they have courses at the Budapest semesters that we don't have here. And the nice thing is, some of these study abroad programs, you go abroad and you screw around and sightsee for a semester and you come back and you haven't really advanced your academic program very much. Here, you go abroad and you're going to work, don't get me wrong, but you're also going to see some pretty cool stuff. Budapest is a really important historical city, and you're going to work hard and you're going to come back and you're going to have advanced your degree, you're going to have made progress towards your degree, and you're going to have lived in a really beautiful place, deeply historical place. So if you want to declare a major, you can talk to anybody in the math department. They're all going to talk to you with the caveat. We have this course called Introduction to Higher Mathematics, which runs every semester, every year in the spring. And it's what happens after calculus is math kind of changes a little bit. It gets much more involved with proof and theory than it does with calculation. And to help you with that transition, we have this course called Introduction to Higher Mathematics. And it serves two purposes. It helps you get into that higher level mathematics, but it also lets you know whether math is something that you might actually be interested in. Because so far, all you've really seen is calculus. And there are areas of math that are dramatically different from calculus. In fact, most of math is actually different from calculus. So you'll get in there and you'll say, this is not really for me. And maybe you'll go major in something else, and that's fine. The only thing I want to mention about that is to be a math major, you have to have a B- or above in that course. And so if you go and you talk to somebody in the math department and they sign you on as a math major, they're all going to tell you, I'll sign this paper now, but you have to get a B- or above, or we're going to have to come back and we're going to have to get you a different major like math physics combined or math econ or sociology or art history or something like that. Okay, so you can sign with a major advisor right now if you want, but you may, if you don't do well in that class, of course everybody in here will do extremely well in that class, so I'm not worried about that. But if you don't do well in that class, then you're going to be forced out of the math major because you haven't met that requirement. Okay.
Is it supposed to be like difficulty on par with this or like level higher?
It really depends on where your head is. Some people find Math 260 really easy, and other people just, it's just so different from what they're normally used to that they struggle with it. So it does depend on where your head is. I would say if you think you're a good abstract thinker, then you're going to be fine there. I would say that if you don't think you're a good abstract thinker, that doesn't mean you aren't one. It may just mean that you haven't explored that side yet in a very deep way. Almost done. Senior project. So another thing here we do at Whitman is the senior project. You can go to math.whitman.edu and then go to the real web page there, and then go to the senior project archive. And every year, our senior math majors are paired up one-on-one with a member of the faculty, and they work on independent study projects. And here's you can see a list of things that we've done with our students over the years. Most of this stuff doesn't get published; it's just internal documents. But I worked on a paper with Robin Miller last year. She's since moved on. She was a senior, and we're working on a manuscript here, and this is likely to get published sometime in the next few months. So sometimes you can actually get something published out of this, but feel free to look through that and talk to any of us in the department about the major if you're so inclined. There have been some famous math majors like Gauss, Euler, and so forth, and Michael Jordan was a math major. Bram Stoker was a math major. On the downside, Ted Kaczynski was a math major. You know who Ted Kaczynski was? The Unabomber, that's right. Yes, so even mathematicians can go wrong. Another one that you may not know, Paul Wolfowitz. I consider him infamous, although that's more of a political leaning than anything. Paul Wolfowitz is the guy that sort of engineered the whole rush into Iraq in 2003, back when you were just wee. Okay. Not you though. Okay, I'm done. Let's talk math here for a while. Let me switch over. Yeah, plenty of time. All right, so what we want to talk about today are triple integrals. And cylindrical and spherical coordinates. And what I want you to do is I want you to recall from double integrals that dA was equal to dy or dx dy in Cartesian coordinates, and that it was somewhat stranger for polar coordinates. Okay, and so dA for Cartesian coordinates was pretty straightforward. It was dx dy, and we imagine that as just being a tiny distance in the x direction and a tiny distance in the y direction, describing a tiny little piece of area, and the area of that little tiny piece of area was dx dy. And then we started talking about polar coordinates, and in appeared this little lowercase r. And do you remember why we had to do that? Why is the polar coordinate little piece of area so much more complicated than the Cartesian little piece of area? Nick?
Because instead of being a square, it's like a...
It's this weird thing, right? But more than that, what happens to this thing? It changes size depending on where it is, as opposed to the Cartesian one where it's just the same size everywhere you go in the plane. This guy gets bigger as you go out, and it gets smaller as you come in. And the exactly right scale factor to compensate for that is this r. Okay? So the area is much larger when you're away from the origin, when you're r away from the origin, and you just scale it by r. Or it's much smaller when you're really close to the origin, scale it by r. So that's the right thing to do. What I'm going to try to, in a hand-wavy, non-mathematically sound way, I'm going to try to describe to you what dv turns into in triple integrals. So now let's consider dv in different coordinate systems. Okay. So Cartesian, you already know. dv is just dx, dy, dz. And as I alluded to earlier, I think you guys already have a pretty good idea of what cylindrical looks like. But I'll try to rationalize this for you a little bit. So remember how we generated the cylindrical coordinate system to begin with. We started with the polar coordinate system, and then we did the dumbest possible thing. We just added on z. So it's polar down here, and essentially it's Cartesian in the z direction. So it's a real sort of Frankenstein of coordinate systems. And you can see that here. This is the area element in polar coordinates, r d theta. So that's this little piece of area. And now we have this Frankenstein coordinate system where we just tack on the z coordinate. Well, what's that going to do? If we thicken this up by a little piece of dz, then the volume that you get from that is just the area of the base, which is r d theta, times the height, which is dz. And that little chunk of volume now, that slightly fattened little sector, as you go out gets big, and as you come back gets small. So there's nothing different really there. We've just tacked on this extra coordinate. And as with the Cartesian dv, you can shuffle these guys around and get the same result. So the order of integration doesn't matter. But you have to have this little r in here. Otherwise, it's not going to work. It's not the correct volume element. Okay, so if you thought that was bad, that is the volume element in spherical coordinates. And again, I'm not going to try to really rigorously explain this. I'm going to do some hand-waving qualitative kinds of descriptions, and then we're just going to go on and do some problems. But let's first remind ourselves, since it's been a while since we did spherical coordinates, what does the variable rho represent?
Distance from the origin.
Distance from the origin, exactly. Do you remember what the variable phi represents? So the angle from the North Pole, kind of, or from the vertical, yeah, out. And that's measured in radians. So what's the range of phi that covers the whole? 0 down to pi. That's all you need to cover. So that's all phi needs to do, is go 0 to pi. What's the range of rho from 0 out to infinity? Okay, and then what's the third variable, theta? What does that do? It's a little harder to describe. Yeah, it's like the angle around the equator. I couldn't have said it better myself. So the angle around the equator, and in order to describe, for example, a whole sphere or all of space, theta needs to go from 0 all the way to 2 pi, all the way around. So that's the natural range of these three variables. Now, of course, they're all periodic, so you can have negative phis, and you can have phis that are past pi, and so forth, and that all still makes sense. But the most natural range of these variables is as I just described. Okay, I'm going to pop over to the book and try to motivate a little bit why this volume element looks the way it does. So there's this figure in the book that shows you what a little piece of volume looks like in spherical coordinates. You can kind of see that, right, this guy is a distance rho from the origin. And as rho gets short and this guy moves in along these rays, you can see that it shrinks dramatically. And in fact, it shrinks, its volume shrinks more dramatically than the polar guy shrinks. It shrinks like rho squared instead of just plain old, like, see here we only have an r. Here we got a rho squared. So rho has much more power to shrink and expand volume than r does in polar. Okay, these relationships are really just, they just follow from a careful consideration of the trigonometry of the situation. So you look at one of these little volume elements. So here's a little volume element. And what we're doing is looking at it from the side. Here's the z-axis, and here's the xy plane down here. You look at it from the side, and you do the trigonometry, and you can get these approximate side lengths. And then you look at it from the top. And so this length from the top is rho sine phi delta theta. That's this arc length. And this length from the side is rho delta phi. That's this arc length. And then this distance here is just delta rho. How do you get the volume? How do you get the approximate volume? You just multiply this times this times this. So this is one side, this is the other side, and then you don't see it here, but there's this side out here. Okay? Take those three things, multiply them together. You notice you have two factors of rho. That gets you the rho squared. You have a sine phi, which really just follows from this trigonometric relationship down here. You get a sine phi, and then you get a delta rho, a delta phi, and a delta theta that all multiply together. And then when you plug them into the integral, the deltas all turn into d's. D rho, d phi, d theta, and that's where this comes from. Okay, that's as far as I'm going to go with that. We will talk a little bit more about this on Monday when we do section 7, I think it is, the change of variables theorem. We'll talk a little bit more about this, but for now, we'll just leave it. I do want to remind you, however, oops, and I want to spell remind, from section 12.6, I think it's 12.6, the spherical coordinates look like this. So these are the spherical coordinate transformations. So x is equal to this, y is equal to this, and z is equal to this in spherical coordinates. And then also there's cylindrical. Which you probably are more familiar with. Where we just tack on z. Why are we going to need these relationships? Well, when we're converting these triple integrals to spherical coordinates, anytime we see an x, y, or z, we need to replace that x, y, or z with these formulas here. Or when we're doing cylindrical, same thing. Anytime we see an x, y, or z, we need to replace them with those formulas. Okay, the real trick with this section and the new skill that you're learning is, and it's really the skill that you've been developing through this whole chapter, is how to describe these regions of integration using the coordinates that you're given and using the equations that you're given. So the new skill for today is you've got these regions of integration, and now you need to describe them, or you need to learn how to describe them in cylindrical coordinates and in spherical coordinates, as opposed to simply Cartesian coordinates. And with that, for the rest of the period, what I'd like to do is just a sequence of examples. And the first example you can probably guess, or maybe you won't guess, but you won't be surprised by it. Yes. So let's compute the volume of a sphere of radius A. I don't know how many times we've done this now, but you know, it never gets old. Volume of a sphere of radius A. So recall that the volume of any figure is just the integral of 1 dV. Right? So the volume of any figure E is just the integral over E of 1 dV. Except now we're going to try to do this in spherical coordinates. So in spherical coordinates, as we just introduced, dV is rho squared sine phi d rho d phi d theta. All of that just from a dV. But the task now is to describe the sphere of radius A using to set up the limits of integration to describe the sphere of radius A in these three variables, rho, phi, and theta. So let's take them in order. We're doing rho first. So where does rho start and end for a sphere of radius A?
0 to A.
Absolutely. And phi? 0 to pi. And theta? 0 to 2 pi. Absolutely. Okay. This is a massively separable integral. So I can actually rewrite this 0 to 2 pi d theta 0 to pi sine phi d phi, 0 to a rho squared d rho. Remember what I mean by separable? You can write the integram as separate function, as the product of functions solely of rho, solely of phi, solely of theta. So this is the product of a function solely of rho and solely of phi, and secretly there's a constant theta in there. Theta equals 1. Does everybody see that? I'm not sure that this helps a whole lot. I just like to point it out because sometimes it can save you a little bit. That first integral is just 2 pi, right? Second integral. Now let's do the third one. Third integral, can you do that in your head? What is it? A cubed over 3. Some of you might be able to do this one in your head too. What's the antiderivative of sine phi? And then we want to evaluate that from 0 to pi. What's that all work out to? Yeah, 2. And we get the not surprising formula, 4/3 pi a cubed. Probably of the 3 that I've done, I think I've done this in Cartesian, polar, and now spherical. Of the 3 that I've done, this is probably the easiest one. And there's a reason for that. We're doing this problem that has a lot of spherical symmetry to it, and we're doing it in what I would call the correct coordinate systems. Okay, let's do a slightly less obvious one. I realized this morning when I was writing up my notes, I've written down these problem numbers like 15.62, and all I wrote was parenthetically spherical, or 15.66 cylindrical. And then I got into class at 1, and I'm working these problems, and they're not working out. I'm like, what the heck's going on here, you know? And yeah, I tried to do the problem in spherical, and it really should have been cylindrical or whatever. And I downloaded, I was using an old version of the book, and the problems apparently had shuffled around, and I just didn't, anyway. So I have the new version of the book here, and I have the old version of the book in my office, and so that was not a good thing. We survived. I'm not sure how clear it was, but we survived. I survived anyway. So let's go back to the book here and just pick a few of these problems. It's not really important that I do 2 or 6 or what have you. It's just that we do a few of these. Let's try 2 because it just looks really scary. What do you think? You're going to have to do a lot of these problems and sort of develop an intuition, but what do you think? Spherical or cylindrical?
Cylindrical.
Yeah, you might think that. No, seriously, let's just explore this a little bit. So the cylindrical people, why? Okay, before we go there, let's see if we can figure out what this actually describes. Is it an ice cream cone? Wow, you're so fast. Z goes from here to here, right? So it starts out on this right angle cone, and it ends up on the sphere of what, radius 2? Root 2, yes. I'm having issues with that today. Down here in the xy plane. So down here in the xy plane, y is going from 0 up to the square root of 1 minus x squared. That's the circle of radius 1. It's the top half, and then from minus 1 to 1. So it's the top half of the circle of radius 1, and then the volume between the sphere of radius root 2 and the cone, the right cone. Good. And then I don't really care about the integrand, but it does look like that integrand will be nice in spherical coordinates, right? Okay, let's see if we can't manage this. So let me try to sketch this just a little bit anyway. Wow, terrible drawing today. Starting over. All right, so there's the ice cream cone. And I guess we've determined down here that this is a, this is 1 here, and this is -1. Yeah? And then if we look at it from the top, we're only doing the upper half. So it's a vertically sliced in half ice cream cone. All right. Can you describe this figure for me in spherical coordinates? Let's start with rho. So I'm going to fill up the space with rays from the origin. Can I do that easily? Well, let me draw some in there and see if you believe me. Somebody said yes, and I agree. Right? If I draw those rays in that go from the origin out to the sphere, they're always starting where? 0, and they're always ending where? Which is what did we decide? Root 2? So they're always ending on the sphere. And I think we decided the sphere had radius root 2. No? Yeah. So rho goes from 0 to root 2, and I don't want to write in red anymore. All right. Here's where it gets, I think, interesting. What angles phi from here, measured from here, what angle phi describes that figure? 0 to pi over 4, absolutely. Okay, now theta. Here's theta. 0 to pi. Yeah. Okay, let's go look at the integrand. What's the integrand? It's just rho, right? The distance from the origin. And then don't forget all the nastiness that comes with the spherical dv. That's rho squared sine phi d rho d phi d theta. That's a fairly manageable integral, eh? In fact, it's massively separable again. We get a pi from theta. You can probably do the rho in your head, right? It's rho to the 4th over 4. Plug in root 2. Yeah, so this is all good. I'll leave that to you to finish. I think it would be instructive at this point in your spherical integral careers. It might be instructive to see what that looks like if you tried to do it with cylindrical. I think, and this is where it all went off the rails at 1 o'clock. I tried to do this in cylindrical, and I ended up getting something that would be a really painful integral to do. And then I realized that the two problems that I had been thinking about were different. Anyway, so spherical. But look at it in cylindrical just to see what it looks like. It might be instructive. Let's do another one here. Let's try to find one that's actually. Let's do. What's the difference between 5 and 6? Oh, I see. Let's do 6. You can probably guess. You can probably guess what I think is the appropriate choice here. But what do you think? What's the right choice? Cylindrical or spherical? And you don't have to decide now. Here, let's talk a little bit. This thing here. So we're doing. What did we decide? 5 or 6? 6. 6. Okay, so this thing here, what is that in the XY plane? I'm going to put a note here just so that I don't get confused. We're doing that one. What is that in the XY plane? It is a circle. Can you be more specific? Center, radius? Not 0, 0. Close. 1, 0. Yes.
What's going on? Why is 0?
It's 1, 0. Okay, so how do you see that if you're not seeing that just by staring at it? Let's go back over here and look at x squared minus 2x plus y squared equals 0. X minus 1 all squared plus y squared equals 1. What's that called? Completing the square, exactly. It comes back. Okay. Do you remember what this looks like? I'm going to do this in cylindrical. Oh no, I gave it away. Damn it. Do you remember what this looks like in polar coordinates? This circle. It's a terrible circle, but there you have it. So that's what this looks like in the plane. Do you remember how to describe this thing in polar coordinates? It's like cosine theta, but not quite. 2 cosine theta, exactly. So this guy is r equals 2 cosine theta. What if you can't just stare at that and see that? How could you figure out that that's what r is? R is equal to 2 cosine theta. I can plug in the polar forms for x and y. So I could plug in r cosine theta here, r sine theta there, expand it out, and what's going to fall out essentially is r equals 2 cosine theta. You might have to hit it with a trig identity. I'm not really sure, but you get the idea. Okay. Actually, I don't think you do, now that I'm looking at it. Let's look at the other thing. So the other thing is under x squared plus y squared plus z squared equals 4, sphere of radius 2. Let's sketch that into the picture. And by sketch that into the picture, let's see what it looks like in the xy plane. So the sphere is actually up here. And then there's this thing here, which you can think of as kind of a cylinder coming up and cutting a piece out of the sphere. So we're trying to figure out what that volume is. What's the volume inside this cylinder, above the xy plane, in the first quadrant, below the sphere? Yeah. Still with me? Okay, we're going to go cylindrical. Oh, I'll label these for you. X, Y, and Z is coming out of the board. All right. So let's see if we can't describe this region in cylindrical coordinates. So I'll leave some space here for limits. What's x and y in the integrand? Yeah, in cylindrical. So I've just got to do like r squared cosine theta sine theta, right? And then you have r dr d theta. Oh, and there's a dz also. Okay. What's z going to do? Z is going to start off down here and go up to the sphere, right? So z is going to go from 0 up to, let's start out with this, right? Isn't that what z is going to go up to? Or is it 4? I can't remember. That's what z is going to go up to. What's the problem with using that as the upper limit in a cylindrical integral? I can't use the x and y's. So what does that look like in cylindrical coordinates? 4 minus r squared. Now we're okay. Does everybody get that? Okay, let's keep going then. dr. So now r and theta are describing this little shaded region in the xy plane. So if you think about that in terms of rays, you're always starting here and ending up here, right? So what are the limits in the r integral? 0 to 2 cosine theta. Don't want red. All right. And last, theta. What range of thetas describes that upper 0 to pi over 2? Good. Some people want to knee-jerk and say that that's 0 to pi because it's the upper half of a circle, but it's 0 to pi over 2 because, well, why? When theta is equal to 0, you're out here, right? And as theta increases up to pi over 2, r decreases down to 0. And so that's why those limits are what they are. All right. I don't know. Is that a manageable integral? What do you think? The z integral. Let's think about z. If we do z, we're going to introduce. If we do z, we're going to introduce a root 4 minus r squared, right? And then if we do r, ugh, that's going to be nasty. R cubed. Probably just, I don't know, hack away at it with integration by parts. I don't know. This is not a spherical problem.
You could put the r squared and convert it into cube using the 4 minus r squared.
Oh yeah, I remember that one. Yeah, what is that called? That's a different kind of substitution. Oh, is that I can't remember what that substitution is called. Yeah, this is doable. Hold on for a second. It's been a long time since I did that kind of integral. So let's do z. I don't really want to do this right now, but let me give it a shot here. So we do z. So I'm going to pull that guy out. This guy is 0 to 2 cosine theta. We've got an r cubed, right? And then we've got a square root of 4 minus r squared. Yes, gosh, what is that substitution? Minus r squared dr, and then I've already done z, right? Okay. Oh, and I can't separate that because that cosine is there, so oh well. Sorry about that. Actually, I probably could separate it, but let's. Okay, doing that r integral. You can let, like Katie was just saying, and it's been a while since I did this kind of substitution, but you can let u equal 4 minus r squared, and then du is equal to what? Negative 2r dr. Okay, and then r cubed. Can I get my hands on r cubed? Okay, so now what I can do is take one of these guys, right? That is r squared r, and I can take this guy and do this and grab and do that. And now what's left is r squared, and I can solve for r squared here. So I'm not going to do it totally out, but I can solve for r squared there, right? And I can drop in 4 minus u, and now I have 4 minus u sitting here and a root u sitting here, totally manageable. So that's the substitution. Thank you. Okay. I think we're good. Any questions before we break? Okay. Have fun with these. Perhaps I'll see you Sunday night at 8.
Yes.